So you can see the PPT, right?
Yes, sir.
Okay, so the question is like this. We basically have a reinforced concrete beam, 250 millimeter wide and 400 millimeter effective depth. The width and depth of the beam is given. It is actually subjected to a ultimate design shear force of 150 kilonewton at the critical section near the support. At the critical section near the support. Okay, so the tensile reinforcement near the support is 0.5%. The tensile reinforcement, that is the longitudinal reinforcement in the beam at the considered section, is 0.5%. You are supposed to design the shear stirrups. Okay, also design the minimum shear reinforcement at the midspan, assuming M20 grade concrete and Fe 250 grade steel. So basically, in this question, you are provided with a beam, a section. So let us assume that the flexural design of this section is already completed, and basically what you have is, you have a beam like this. Okay, and the sectional dimensions of this beam is, the effective depth D is actually given as 400 and your B is 250. Okay, D is from here to the level of reinforcement. Okay, and the critical section is, they have directly given the shear force at the critical section. So let's assume that from the face they have taken D distance, and we have the critical section here, and the V, is it V or VU given in the question? It is VU, because it is mentioned that the ultimate design shear force. Design shear force means it is a factored value, that is VU, which is given as 150 kilonewton at the critical section. Again, one more thing is given, the amount of main reinforcement or the flexural reinforcement at this particular section is 0.5%. That means AS by BD is equal to 0.5. Okay, this is also given in the question. Then what? We are supposed to design for the shear reinforcement at this particular section. Okay, so these are the data given in the question, and let's see how to find it out. So first thing is that we have to check whether we require to provide minimum amount of shear reinforcement, or we have to actually perform the design of the shear reinforcement, or we have to redesign the provided section. How to do this? For this, we need to find out the value of tau V. Then we have to find the value of tau C. Also, we have to calculate the value of tau C max. So the first step is, you have to see what are the data given in the question. Then we have to find out the normal shear stress, that is tau V, which can be calculated by VU by BD. That is the tau V at this particular section. Please note. Okay. So VU by BD. Then we have to find the value of tau C and tau C max from table number 19 and 20 given in page number 73 of IS 456/2000, based on the which value, 100 AS by BD, and the grade of the concrete. Here the grade of the concrete is M20 grade. Okay. So once you have that, then what do you have to do? If shear reinforcement is required, find the value of VUC. How to ensure that, or how to know that whether we require shear reinforcement or not? Suppose when we calculate tau V and tau C as well as tau C max, the condition is like this: tau V is greater than tau C, and this tau V is again less than tau C max. If this is the case, we have to provide shear reinforcement. So in that case, we have to calculate the value of VUC, that is the shear force that can be taken up by concrete. How to find VUC? VUC will be equal to tau C, the stress that can be taken up by concrete, into B into D, stress into area, that will give the force. Then how to find the amount of shear force that should be carried by our stirrups? Yes, stirrups. How to find this? This will be actually VU minus VUC. Okay, so once you find out the value of VUS, then we have to find the spacing of the stirrups based on the value of this VUS and the assumed diameter and legs of the stirrups. We may assume 2-legged 8 mm stirrups, and we can calculate the area of 2-legged 8 mm stirrups will be 2 times pi by 4 into 8 square. Okay, so this will be the AST value. Let us take the grade of the stirrups as 415 itself. So And after finalizing these things, we can find the value of spacing also. Okay, so this is basically the table number 20, not 20, it is table number 19. And the data is given are B, D, AST by BD is given in this question. It is 0.5%. Therefore, the decimal value will be 0.005. Now, tau V can be calculated by VU by BD, and VU is directly again given in the question, but please note it was given in kilonewton. So this is another area where students usually commit mistake. When the units are different, you have to always convert it into newtons and millimeters, then do the problem. Okay, so 150 kilonewton into 10 cube, which you convert that to newtons. Then we have 250, it is in millimeter, 400 again in millimeter. So this will give our tau V as 1.5 Newton per mm square. പിന്നെ ഒരു കാര്യം പറയാനുള്ളതെന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ നിങ്ങൾ പരീക്ഷയ്ക്ക് ചെയ്യുമ്പോഴേക്കും കിട്ടുന്ന വാല്യൂ ഒന്ന് കോമൺ സെൻസ് വെച്ച് ആലോചിക്കുക. ചില സമയത്ത് നമുക്കറിയാം ടൗവിയുടെയും ടൗസിന്റെ എല്ലാം വാല്യൂ അത് നിയർലി അറൌണ്ട് 1 ആയിരിക്കും, അല്ലെങ്കിൽ 2, മാക്സിമം ഒരു 3, അതിന്റെ അപ്പുറം ഒന്നും പോകില്ലെന്ന് അറിയാം. ചില സമയത്ത് എക്സാമിന് കാണുന്നതെന്ന് പറഞ്ഞാൽ ദേ വിൽ ബി ഗെറ്റിംഗ് ദ വാല്യൂ ഓഫ് ടൗവി ആസ് എ 15 or 15.87. They will directly take this value and proceed. So please apply your common sense. When you see such values itself, you have to understand that there is some mistake happen. Okay, so please try to look into that. And once you calculate the value of tau V, tau C can be taken from your table. Okay, table number 19. So in this particular case, you can see that tau V is coming as 1.5 Newton per mm square, tau C is coming as 0.48 Newton per mm square, and tau C max, again from table number 20, it is obtained as 2.8 Newton per mm square. So basically the condition here is our tau C is less than tau V, and this is again less than tau C max. So we have to design for shear reinforcement, and shear reinforcement is necessary. So for performing these checks, you will have some part of the marks for your university examination. In point of university examination, if you complete up to this point, you will get some amount of your credits. Okay, this is how they will split the marks. Now what? Now you have to calculate the value of VUC, and then you have to find the value of VUS. For this also you will be having some amount of marks. Then the remaining marks will be for the actual shear design. Okay. So VUC can be calculated as we mentioned, tau C into BD, that is coming around 48,000 newtons. Therefore VUS, that is the amount of shear force that should be carried by our stirrups. How to find that? That will be equal to the total shear force, that is 150 kilonewton or 1540 Newton minus this value, the amount of shear force that can be taken up by my concrete section, and this is the value of shear force that should be resisted by my stirrups. Now what I will do is that I will assume that I will be using 2-legged stirrups of 10 millimeter diameter. Therefore I can find out the corresponding area, that is 2-legged. So therefore 2 into 5 by 4 into 10 square. Now I will use the respective equation and find the value of SV. SV is the spacing between the stirrups, and I will also check it with the maximum spacing, and this thing we have already seen, maximum spacing can be the minimum of 0.75 D or 300 mm. For this check also there will be some credit of the marks. Okay. So once that is satisfied, finally we have to give, hence provide 10 millimeter diameter 2-legged stirrups at 130 mm center to center spacing in this case. So that completes the first part of the question. That was the design of shear reinforcement at the critical section. In a similar fashion, you can perform the, you are also supposed to find out or perform the design for minimum shear at the, say also design the minimum shear reinforcement at the mid-span. It is directly mentioned that you can go with the minimum reinforcement at the mid-span. So you know, as per clause number 25.1.5.6, I hope that was correct, or 25.5.1.6. You please refer the correct clause. And there you have this expression ASV by B into SV, that should be greater than or equal to 0.4 by 0.87 Fy. And you have already finalized the legs and diameter of the bars, that is 10 mm diameter and 2-leg stirrups. So you have to use the same area here. Say for a single beam, you have to always provide same type of shear reinforcement. It is not like you can provide some diameter and some number of legs at the support and another thing at the mid-span. It is not a practice of using different types of things like this for a single beam. Okay, so please try to use the same thing. So at the mid-span, yeah.
Diameter
10 mm diameter. That we assume. Normally stirrups 12 mm vareka kodukkarundu. So from 8 to 12 you can assume that is based on the amount of, so nammal practice ആയി കഴിയുമ്പോഴേക്കും നമുക്ക് ഈ വാല്യൂ കാണുമ്പോൾ തന്നെ ഒരു ഐഡിയ കിട്ടും. അതായത് ഇതല്ല VUS, അതായത് എത്ര എമൗണ്ട് ആണ് നമുക്ക് റെസിസ്റ്റ് ചെയ്യേണ്ടതെന്ന് കാണുമ്പോൾ നമുക്ക് based on our practice we will get an idea. Say 2 leg 8 mm will do for this value, or 2 leg 10 mm will be sufficient for this value. That is based on experience. Okay, അപ്പോൾ അങ്ങനെ വരുമ്പോഴേക്കും നമ്മൾ അത് ചെയ്തു നോക്കാം. In case you don't have experience, you are just starting now, so what you can do is that you just try with 8 mm, 2 leg 8 mm bars, and what will happen is that you may be getting a very low spacing, very congested spacing. In this case, SV is getting it as, they are actually using 10 mm bars, and again they are getting it as 134 millimeters. Please visualize that length, 134 millimeters, 13.4 centimeters. That is less than your small scale. You will be using a scale, right? It is actually less than that. So that is somewhat okay. But suppose you are getting a dimension like 50 millimeters. That is 5 centimeters between the shear reinforcements. That is actually very difficult to cast. We have to actually create this cage, right? It is actually very difficult. So what do you have to do? In that case, either you can increase the number of legs, or you can increase the diameter. Say sometimes I may be using trying with 2 leg 8 mm stirrups, and finally I will be getting a spacing of say 40 millimeters. So that is not a practically possible thing. So what I will do is that I will either increase number of legs, or I will increase the diameter of bars. That is how we will arrive at the final value. Is it clear?
Yes, sir.
Okay. So for providing the minimum shear reinforcement, we can utilize this equation, use the same diameter and number of leg as we provided in the critical section for our ASV, then find the value of SV. And similar to here, we will finally write, so at midspan provide 10 mm diameter 2 leg stirrups at 300 mm spacing. Again here you have to perform that check, that is 0.75 D and 300 millimeter. Compare that spacing with the spacing which you calculated from this expression. So today it's time, so we will do this problem actually in the next class. So please start doing it. So I will just give an overall idea, say as we discussed now. So first of all, we have to calculate the nominal shear stress tau v. Then we have to find the value of tau c and tau c max from table 19 and 20 of IS 456. Then we have to check whether shear reinforcement is needed or not. If it is not needed, that is the condition is like tau v is less than tau c, we have to go with minimum provision for minimum shear reinforcement. Else, if tau v is actually greater than tau c and tau v is again less than tau c max, we have to actually design for shear reinforcement. And in that case, we will be in need of calculating VUC as well as VUS, as we discussed now. Then, based on the type of shear reinforcement that you are going to provide, whether it is vertical stirrups, inclined stirrups, or in this case, we don't have any bend up bar, so we cannot go with the third option. So you can decide that, and you can assume some number of legs and diameter, then you can design the actual spacing. So that is the design of shear reinforcement. So if the case is the third one, that is tau v is actually greater than tau c max, then what was our option? We have to actually redesign the section. There is no other option for us. Okay, so please find the value of tau v, tau c and tau c max. And once you complete, please tell me, so that we can verify the answers and proceed. And in this case, please note, in the question, the dimensions are directly given, and the given value, ultimate design shear force, is directly given, that is 150 kilonewton. Sometimes you will be provided with the load. All of you please listen now. This is another change that can come into picture. Sometimes you will be provided with just the loads acting on the structure. So in such case, what do you have to do actually? So let's discuss that also. Suppose I am having a beam. So I am having a beam like this, and as per the question, you have a load of say 100 kilonewton acting at the center of this beam, and the length of the beam is given as 10 meters. Okay, and it is mentioned that this is simply supported. So, and you are supposed to design this beam. Say you are supposed to design at two locations. One is at the critical location, critical section, and another one is at the midspan. So in these both cases, what you have to do is that, as the first step, first of all, you have to calculate the amount of shear force, that is V coming at the required section. Say let us assume that we are going to design shear reinforcement for this section. So based on this condition, you will have initially you will find out the reaction at say A and B. Then you know how to find out the value of shear force at any location. So this is my location, which is at a distance of small letter d. That is the effective depth. Let us assume that the effective depth is 200 millimeters. So this will be 0.2. Okay. So you just find the value of V coming at this particular section. Then you have to calculate the value of VU, which is your ultimate design shear force or the factored shear force, which can be obtained by multiplying the factor of dot factor, that is 1.5 with your shear force, actual shear force. So this will give you the value of VU. Then you have to proceed. But in this particular question, this value is actually directly given. That is nothing other than this 150 kilonewton. So you please proceed. And again, this 0.5 is the percentage of steel acting at the critical section. That is 100 AST by BD value. 100 AST by BD value. Okay. Now please proceed and tell me the value of tau C, tau V as well as tau C max. You need to refer to IS 446. Tables are there. So that's how you can find out the value of tau C and tau C max. And in between, if you have any doubts or confusion, please clear it now. Please feel free to ask me. I am ready to explain any number of times. That is not a problem for me. So if you have any sort of doubts, please do ask it. Okay.
So tau C is 0.48.
0.48. Yeah, right. That's correct. Tau C value is 0.48.
Max is 2.8.
Tau C max is coming as 2.8, right? Okay, fine. Then what about tau V?
Tau V is equal to 1.5 Newton per millimeter square.
Okay, excellent, excellent. That's the same value which I have also obtained in this particular case. So anyway, so what is the condition here? Here, if you see, tau V is actually less. Tau C is actually less than tau V. Tau V is actually greater than the capacity of our section. But again, tau V is less than tau C max. So basically, we have to go with design of shear reinforcement. Okay. So let us assume vertical stirrups to be provided in this particular case. And for the sake of getting common answer, let us assume 2-leg 10 millimeter diameter stirrups. Okay, 2-leg 10 mm dia stirrups. And one more thing I would like to share with you. All of you, please listen for a moment. See, when you are designing a structure, suppose I am assigning 10 people to design same condition with the same condition. Their answers may be completely different. They may be presenting 10 different answers, but this all 10 answers can be correct. Only thing is that must be safe, that must be economical, and we have some conditions as suggested by our code. This should be satisfied. That's all. But again, say in this case, I will just give an example. Say if I am asking 2 people to design this same problem, say first person may have designed with a vertical stirrups. Second person may have designed with an inclined stirrup. So these design answers are entirely different thing. And another possibility is that first person may have used 2-legged 8 mm stirrups, and second person may have used 2-legged, say 10 mm stirrups. So then also the final answer is different. So for design problem, there is no particular specific answer. The answers can be different, but only thing is that you please understand the concept and the procedure and follow that. That's all. So you can proceed. So now we are moving on to the design of shear reinforcement, and we are designing vertical stirrups. 134 mm, yeah, okay, 133.97 mm. Okay, so how much you will provide? So you have obtained some answers, right? 134 or 133.97. So as an engineer, what will be the suggested value by you? 134 we will provide. 134 we will provide. Okay. 134. I have already explained one thing in one of the previous class. 135. It is a little bit okay. 134. Say, I hope all of you maybe maybe 130. Yeah, excellent. That was the answer which I was expecting actually. Say 134 or 135. That is in mm. I hope all of you have seen how these people actually make these cages in field, right? 134 mm means it is 13.5 centimeters. Do you think that they will be making these reinforcement cages in that precision? No, they will not do that. And even if they are tying this reinforcement in that position, once you shift this thing to one or other location, they may slightly shift the location, means slightly lift the initial position by 1 or 2 centimeters. So that those things can actually happen in the field. So always it is better to round it off to some rounded figure in maybe in centimeter. In the case of stirrup spacing, maybe in centimeter. So 130 means it is 13 centimeters. That is okay. That is a rounded off figure. So it is always better to represent your final spacing in such a manner. And one more thing you have to take care is that once you, in this case, you have obtained a value of 134, right? You cannot round it up, because once you round it up to 140, what happens is that the spacing between the stirrups is actually increasing. Okay, so in that case, the minimum requirement may not be satisfied, because in this particular critical section, you require spacing of 134. That is, stirrups must be that much close enough in order to just resist the amount of shear force that is coming at this location. So once you increase the spacing, it is like decreasing the amount of shear reinforcement. So the section may fail. So in such case, what you can do is that in the view of your safety, you can just round it down, maybe to 130 or maybe to 120. That is also okay. But only thing is that you have to perform the check for minimum spacing and maximum spacing. So if someone is having confusion, let's fastly go through this procedure, which is shown in the slides. So basically, we have to calculate the value of VUC, that is the capacity or the shear force that will be resisted by my concrete section, which can be calculated by tau z into BD, and this value is obtained as 48,000 newtons. Then I will calculate the amount of shear force that should be resisted by my stirrups, that is represented by VUS, which is given by total shear force, that is VU, minus the shear force taken up by my concrete, that is VUC, and it is coming around 102,000 newtons. Now, as we assumed, we will be using 2-leg 10 mm diameter stirrups. So basically, by substituting the values in the equation, corresponding equation for vertical stirrups, we can easily find out the value of SV, and in this case, it is coming approximately around 134 millimeters. And as per the code, the maximum spacing should be restricted to 0.75D or 300, the minimum value in these two. Okay, so basically you have to calculate both of this and compare that with the value of spacing you obtained during your calculation, and you have to always give the smallest value in these three cases. Okay, so in this particular case, you have to write a statement like this: hence provide 10 millimeter diameter 2-leg stirrups at 130 millimeter center to center spacing. Okay, so this is how you should conclude that. And also, as a final result of your any design problem, you have to actually provide a detailed drawing. Okay, drawings are the actual results of our design. Anyway, in the first two modules, we won't be stressing much on these drawings, because you are just learning things stage by stage. But once we do the actual design, the complete design of a structure, we have to actually provide the final drawings. So if in this case, if you are providing the detailing, so what you should draw is, in the question itself, it is given that you have a beam like this is side view, and the length of the beam is the length given in the question? Do we have the length of this beam? I think it is not provided, right?
No, sir.
Okay, anyway, for the final drawing, actually, when you provide the final drawing, you have to show the length of this beam. So for the time being, let's take it as L. And then we have some sort of reinforcements which are provided here. And again, the number of bars or diameter of the flexural reinforcement is not provided to us anyway. Then right now we have designed the stirrups, right? And let me draw one more line here. I will just tell you why I have drawn this line and what is the significance of that also. So once you performed the design of shear reinforcement, you have obtained that we need 2-leg 10 mm diameter stirrups at a spacing of 130 mm C by C at the critical section. So here you have to show some stirrups like this. And towards the middle, I am just increasing the spacing. I will explain why I have done that. And again, on the other side also, I am just making it closer. Okay, then you have to also show a cross section like this. So if you know the number of bars, you can draw it like that. Then you have to also show the stirrups. Okay. Then what you have to do is that you just show like this, put an arrow here, and here what you have to do is that you have to write two-legged 10 millimeter 5 at 130 millimeter C by C. And here also you need to write two-legged 10 millimeter 5 at 130 millimeter C by C. And here the depth, width and other things must be given, and also this reinforcement must be shown. So what is the diameter of this one? Okay, so that also should be shown. You say for this example, let me take it as 10 millimeter 5 reinforcements. All the three are 10 millimeter 5. Then once you complete, say, and again, one more thing is that you just show a section here for your final drawing, and let us mark it as section AA. And here also we have to mark it as section AA, because the spacing of the stirrups at this location as well as the mid span is different. So again at the mid span you show another section. Say let us mark it as BB, and you have to also show another cross section with the same flexural reinforcements. And again you have to show another set of stirrups, but the spacing of this one will be different. Okay, so let's see what is the spacing I am obtaining is 10 mm at 300 mm. Okay, so in this case again two-legged 10 millimeter 5 at 300 mm C by C. So this is the section at BB, and again here also you have to show the value of DB and other things. So this is how your final detailing should be. Okay, and regarding these arrow marks and other things, you have some suggestions or some guidelines from your Indian standard, and I hope you have already got this SP34. So that is actually showing the details of how you can provide the drawings. What are the details that should be included in each type of drawings? In detail, they have provided for beams, columns, beam column junctions, walls, and all the things that we come into means we have in our structural design. Those details are actually given by the code itself. Anyway, for the time being, you just understand we have something called as this detailing as our final result, and we as a structural engineer we have to provide this, and when we do the entire complete design we will look into this in detail. Okay, and again for your examination, once you complete a design like this, you try to provide at least a cross section showing say this one, at least this or this one or this one, any one thing you have to actually show, because some weightage will be sometimes some weightage will be given to this drawing also when you have some questions from your first module or second module. In case of your first module also, you have to draw the side view as well as this cross section. Okay, so now our question have a second part, that is if you go back to the question, I hope these things are clear to you. Is there any confusion in this? Any doubts?
Sir, നമുക്ക് SV 134 millimeter കിട്ടിയല്ലോ, അത് കഴിഞ്ഞിട്ട് നമ്മള് 0.70 or 300 mm maximum spacing എന്ന് പറഞ്ഞിട്ട് എടുത്തിട്ട് 0.75D or 300 mm എടുത്തിട്ട് അതെന്തിനാ നമ്മൾ അങ്ങനെ എടുത്തത്? നമുക്ക് SV ഓൾറെഡി കിട്ടിയല്ലോ.
അത് കിട്ടി. അത് എന്താ ഇഷ്യൂ വരുന്നതെന്ന് വെച്ച് കഴിഞ്ഞാൽ, let's say sometimes what will happen is that I think when you design for midspan you will come into this same thing. So when you calculate this SV, what will happen is that sometimes this value will be higher value. Say sometimes you will be getting it as 302 or 305. Okay, or let us assume it is 320. You are obtaining the value as 320, but code suggests that you need a minimum amount of stirrups to be provided at every section. So that is what is represented by this. You cannot exceed this spacing. Also, based on the diameter, what you have to do is that you have to calculate this 75 into D. What is the value coming? Based on that diameter also, you will be getting some value, and you should not exceed that value also. That is to ensure that some minimum amount of stirrups are anyway, in any case, some minimum amount of stirrups are provided. That should be ensured. That is why code is actually providing such a clause. It is in view of your safety. Is the doubt clear?
Yes, sir. Sir, appo 0.70 edukano adu 300 mm spacing kodukano.
We have to calculate both. We have to calculate both. Say what is the value of 0.75D coming, and we have to also compare 300. Right now we will be having three values. This is my first value. This is my second value. This is my third value. And in this, I have to actually provide the spacing as the smallest one. If this is the smallest, you can proceed with this. If this is not the smallest, in some cases, this may be the smallest value. So in that case, you have to actually provide this spacing. Even though we are getting another value here, we have to actually provide only this spacing. Some cases, what will happen is that this will be the smallest one. In both the cases, you may be having a higher value, but this will be a smaller value. So you have to provide it at spacing of 300 millimeters.
Okay, sir.
Yeah. So that's it. Now you just proceed with the second part. The second part actually states that you have to design minimum shear reinforcement at the mid span. So we have the provision for providing minimum shear reinforcement. We have a equation for that in clause number 25.5.1.6. I think so. Please confirm that. So in that clause, actually, you have an equation like this: ASV by B into SV is greater than or equal to 0.4 by 0.87 F5. Okay, so you please try to use the same diameter for the stirrups as well as number of legs and calculate the ASV. Then from this, what you have to do is that you have to find the value of SV. Okay, so in this case, please see. See, when you work it out, the value I obtained here is 341.6 millimeters. But as per the maximum spacing suggestion from the code, I cannot provide this value because it exceeds 300 mm. So I will be restricting my spacing to 300 mm. That's it. Finally, I have just restricted my spacing to 300 mm. If you see here, it is 300. In this question, actually, we were having a beam which is having a dimension of 300 millimeter by 600 millimeters. So the dimension of the cross section is given here. Then it is told that this beam is actually carrying a uniformly distributed load that is having an intensity of 74 kilonewton per meter. Please note the unit is given in kilonewton meters. Okay. And it is mentioned that this load is actually inclusive of the self weight of the section. Say, whenever we perform the design for concrete sections, you just visualize. Say, for example, the beam which you may have seen in your rooms or in your college, you might have seen a large number of beams, right? So, will it be say if I am asking one of the person to lift that beam, will you be able to lift that? It will be very heavy, right? That means it is having a large amount of weight, and this weight will also contribute to the or will act as a load on the structure. So basically, when we perform the design, we have to actually consider the self weight also as a major load which is acting on the structure. Okay. So in this particular question, this UDL is given as inclusive of its own self weight. So basically, this is a combination of the actual load acting on the structure as well as the self weight of the structure. And it is mentioned that this is acting over an effective span of 6 meters. So the span is given as 6 meters. Then we have 5 bars provided as the reinforcement in this one. 5 bars, and the diameter of the bars are all the diameters are same, that is 25 millimeters. So these are the basic things that is given in the question. So based on this, if we are drawing the section, we have a rectangular section like this. Then the width of the section is given as 300 millimeters, and the effective depth is given as 600 millimeters. That is from here to the level of your reinforcement. Okay, this is from here to here, and here you will be having 5 number of 25 mm bars. Okay, so basically this is 5 25 millimeter 5 bars. So this is what is basically given in this question, and again you have the side view, and the effective span or the span of this beam is given as how much? 6 meters. So let's take it like this. This is given as 6 meters. Then we have a UDL which is acting on this structure, which is inclusive of the self weight, and the intensity is given as 74 kilonewton per meter. So this is what is defined in the first part. And so let's draw the reinforcements also. So for the time being, I am assuming that all the 5 reinforcement are like this. Now let's move on to the next line. Out of this 5 reinforcement, 2 bars can be safely bent up at 1 meter distance from the support. So this is another condition, that is at a distance of 1 meter from this support. Suppose we are moving and reaching a distance of 1 meter, we can easily bend up 2 bars out of these 5 bars. So at this particular distance, what I will do is that I will bend 2 bars and I will extend it like this. And symmetrically on the other side also, I have to do the same thing. So I will be bending 2 bars here at the same location and I will be bending it like this. Here also it is 1 meter. Okay, so this is what is given in the next line, that is out of these 2 bars can be safely bent up at 1 meter distance from the support. So basically we are supposed to design the shear reinforcement. Okay, so when you do such a problem, in actual case, what you have to do is that you have to initially find out the critical section that is at a distance of effective depth from your support. So take a section there, you have to calculate, say take a section at the critical section, then you have to calculate the shear force coming there, then you have to convert that into what? Then you have to convert that into factored shear force, that is multiplied by 1.5. Then what you can do is that you have to perform the design for this section. In addition to that, you have to also design the shear reinforcement at the midspan where your shear force will be minimum. In addition to this, another thing that we have to do is that we have to actually take a section here where this reinforcement are not bent or just about to get bended. Okay, so at this particular section also you have to perform a shear design. Okay, you have to basically perform 3 shear designs here. And normally when you refer some textbooks, what will happen is that in problems from your second module, they might not have considered the critical section. Instead, what they might have done is that they might have taken the support reaction, that is the most critical value of shear force, and perform the design for this much part. Okay, for this much, that is here we have the effect of bent up bar also. So they might have done like that. That doesn't make any difference. Only thing is that it will be little bit uneconomical because this shear force will be a higher value. So when we provide the shear reinforcement, it will be more. That is not actually necessary, but in that way also it will be safe. Okay, so I think I have directly taken the answer from some text. So here also they might not have taken the critical section. They might have performed the shear design at the support. So please keep this in mind. You have to actually perform the shear design at the critical section. Then if you have a bent up bar, you are considering the effect of bent up bars, you have to perform a shear design at a section before the starting of bending. Then you have to also perform the shear design at the midspan. So at least for 3 sections you have to perform the shear design. And please note the question. In the question, nothing is mentioned about this where all you have to perform the shear design. But just in a single sentence they have mentioned that design the shear reinforcement for the beam. So basically you are supposed to perform the shear design at the necessary sections. So basically the data given in the question, grade of concrete, that is M20 grade. Is that was given in the question? No. So once this data is not given in the question, you can make any assumption. See, only thing is that you have to mention there. Say as mentioned here, the grade of concrete here, it is taken as M20 grade and the grade of steel is taken as Fe 450. Instead, if you have taken it as M30, there is no problem. Okay, so that is up to you. Now, what they are doing is that they are just factoring the externally acting load. That is, W was actually given in the question as 74 kilonewton per meter. But here, what they have done is they are just factoring it and converting that to factored load. Okay, so 1.5 times W, that is coming around, in this particular case, it is coming around 111 kilonewton per meter. Now, what they are doing, they are actually calculating the support reaction or the maximum shear force. Okay, you know that the maximum shear force will be at the support, therefore VU max. Now why they have put this U here, VU? Because we have already factored the load and they are using the factored load for calculation of shear. So obviously it will be factored shear force. Since we have already factored the load, it will be factored shear force. Therefore factored shear force maximum or the design shear force maximum design shear force is equal to, you know that at the support it will be WL by 2, that is in this case I am taking the factored load, therefore WUL by 2. So 111 into the span, that is 6 meters by 2, which is coming around 333 kilonewtons. So the maximum amount of shear force that is experiencing here, that is the design shear force, is 333 kilonewtons. So again, please note this, you have to actually perform the shear design at the critical section. Now let's see what they have done here. I think they have actually performed the design at the support. So please don't mind that. Please try to understand the concept in which we have to perform the design. We will draw one more figure here. Okay. Say we have the beam side view of the beam like this, and we have some bars running like this. Out of this, at 1 meter, we have just bent up 2 of the bars like this. Okay. And here also I have bent up it like this. Now, what they are doing is that they have taken a section here. Okay. And they are just finding out how much AST is here. Okay. We require this AST for the calculation of tau C. That is, tau C is calculated from table 19 of IS 456 using 100 AST by BD and the grade of concrete. So we require this AST. So in the first step, they are actually calculating this AST. So we know that 2 bars were already bent up at a distance of 1 meter. So basically here we will be having only 3 number of 25 mm bars. So AST available up to a distance of 1 meter is 5 minus 2, that is 3 bars into pi by 4 into 25 square, which is coming around 1472.6 millimeter squares. And please note, there can be mistakes in these numerical values. You have to do it and find the correct value. Okay. So in most of the text, there can be numerical errors. Please don't mind that. You just try to understand the steps and procedure in which the design is performed. Now, once you obtain the value of AST, you have to calculate 100 AST by BD. Why we are doing all this? In order to calculate the value of tau C. That must be there in your mind. Okay, 100 AST by BD is coming as 0.818%. Therefore, tau C can be calculated from table 19 of IS 456. I hope it was in page number 73. So we don't have a direct value for 0.818. So we have to interpolate that. So you find the previous value and the value next to that. Then you have to form a triangle like this. Then you have to find the value corresponding to 0.818. Okay. So after doing that, for tau C, in this particular problem, you will be getting it as 0.576 Newton per millimeter square. Okay, 0.576 Newton per millimeter square. And from table number 20, we have to calculate the value of tau C max. So tau C max is, in this case, I have used M20 grade concrete. So tau C max is coming as 2.8 Newton per mm square. Okay, now what we should do? For the time being, we have to also calculate one more value. What is that? What is the missing value? Can anyone suggest me which is the missing quantity now? We have to find the value of
Spacing.
Tau V. Okay, tau V is equal to VU divided by B into D. And VU we have already calculated. That is this VU max. Okay, this VU max we have already calculated, and that is coming around 333 kilonewton. So 333 divided by B into D, where B and D are 300 and 600. Okay, substitute that. Yeah, any doubts?
VU
max idano. So basically, when you have a beam like this, say simply supported beam, which is subjected to a UDL of intensity W, and let the span be L. We know that the maximum shear force will be at this location, at the support, right? What will be the value of this reaction? This is symmetrical case, right? So equally this load will be distributed to both the sides. What will be the total load? It will be W into L, which can be assumed to be acting at the center as a point load. So our total load is WL, and we know that this is a symmetrical case. So it will be equally transferred to both the supports. So at this support, we will have a force equivalent to WL by 2, and at this support also we will have a force equal to WL by 2. That is what is written here, WL by 2. Is it clear?
Yes.
Yeah. So once we get the value of VU, substitute that and find the value of tau V. Okay, once we get all these three values, what we can do? We can make the comparison. We can check whether we need to provide or go with nominal, that is minimum amount of shear reinforcement, or we have to design for shear reinforcement, or whether we should go for redesign of the section. So in this particular case, when we check it out, what we will see is that our tau V value, I don't have the value of tau V. Anyway, you can tell me that at a later stage. Tau V will be greater than tau C, and again tau V will be less than tau C max. So what does this infer? What will you do? You have to actually go with design for shear stirrups. Okay, so then the next step what we will do is that what is the amount of shear force that can be carried by my concrete section. These things we have already seen in the previous problem. So basically our concrete section, that is this section, will be able to carry some amount of load, right? Without including the effect of this bend up bar. Okay, please note, without the effect of this bend up bar. That is what we represent by VUC, which is equal to tau C, which is calculated here 0.576 multiplied by B into D, and it is coming around 103.68 kilonewtons. And we know that so basically the VUS is equal to the total shear that should be resisted minus the amount of shear force that can be taken up by my concrete section. Okay, so please give me a minute. Okay, in this problem, so I am really sorry, in this problem actually they are not dealing with this support reaction. They are not calculating tau V based on this VU max. VU max is actually our support reaction. As we told, we are just going with the critical section itself. So we know that the critical section will be, or critical section, or rather than that AST available at a distance of 1 meter. Okay. So basically what they have done is they have taken a section at a distance of D units from the support, that is our critical section. The depth of our section is 600 millimeters. Okay, so basically they have taken a section at 600, D is equal to 600 millimeters, and they have found out the value of VU here. How to find the value of VU here? Say you know that the support reaction is WL by 2, and you have a UDL spanning over this 600 meters. Therefore, VU at this location will be equal to, you have already learned how to draw the shear force diagram, right? So in that, if I want to find the value of shear force acting here, it will be WL by 2 minus W into 0.6. Okay, where W in this particular case is 111. Okay, 111 into 6 by 2 minus 111 into 0.6. That is the effect of this UDL. This UDL is acting in the downward direction, and WL by 2 is acting in the upward direction. Therefore, I will get the net effective shear force that is coming at this particular point, which is our critical section. And in this case, they have actually obtained it as 244.2. I hope it is.
Sir,
yeah.
Okay.
ഏതാ ക്ലിയർ ആതെ VU കാൽക്കുലേറ്റ് ചെയ്തതാണോ അല്ലെങ്കിൽ നമ്മൾ ഈ ക്രിട്ടിക്കൽ സെക്ഷനിലേക്ക് പോയതാണോ?
ക്രിട്ടിക്കൽ സെക്ഷനിലേക്ക് പോയി കഴിഞ്ഞിട്ട് പിന്നെ
ഒറ്റ കാര്യം നോക്കിയാൽ മതി. നമ്മൾ ആദ്യം പറഞ്ഞത് വിട്ട് കളഞ്ഞേക്കും. നമ്മൾ എടുത്തിരിക്കുന്നത് എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ ക്രിട്ടിക്കൽ സെക്ഷനിലാണ്. സോ വി ആർ ഗോയിങ് ടു പെർഫോം ദി ഷിയർ ഡിസൈൻ അറ്റ് ദ ക്രിട്ടിക്കൽ സെക്ഷൻ, ആൻഡ് ആസ് പെർ അവർ കണ്ടീഷൻ വി നോ ദാറ്റ് ദ ക്രിട്ടിക്കൽ സെക്ഷൻ വിൽ ബി അറ്റ് എ ഡിസ്റ്റൻസ് ഓഫ് D units from the face of the support. So let us assume that, say in this case D is 0.6, 600 mm is the depth of the beam. So I am just taking it like this, 0.6, and this will be my critical section. Okay, and at this particular point I have to perform the shear design. So basically, to start with, what I will do is that without the effect of shear reinforcement, I will calculate the value of amount of shear force that can be carried by my concrete section. So before that, first of all, I have to calculate the value of shear force that is coming at this particular section. Okay, and we know that in this beam I have a UDL which is spanning throughout the beam inclusive of the self weight, and we have factored that, and we have found that this value was WU was 111 kilonewton per meter. So basically this intensity is now 111 kilonewton per meter spanning over a distance of, this total distance is 6 meters. Okay. Now what I have to calculate is that I have to calculate the value of shear force that is coming at this particular point. So please note this is factored value now. 111 is factored value. So this will be factored shear force. I have to calculate the value of factored shear force at this particular location. And as per the definition for shear force, you know that shear force is the algebraic sum of all the forces acting to the left or right of your section. Right now my section is this one. So I am considering this left side. Here I have one force acting in the upward direction. Then I have a piece of UDL like this, which is acting in the downward direction, and the intensity of this UDL is again 111 kilonewton per meter. Therefore, what will be the value of VU? In this case, VU will be equal to this upward reaction. We know that this upward reaction is WL by 2. Then we have a downward force, therefore minus W into this UDL should be converted into a point load, right? W into this distance is 0.6. We already know that. 0.6. So this will give you the value of VU. In this particular case, they have obtained it as 244.2. That is the total shear force that is coming over this section, and we have to ensure that this shear can be easily carried by this beam with the help of the concrete section as well as the external stirrups. Is that clear now? Up to this?
Yes.
Okay. Now what we do is that we have to calculate the value of tau c. For that, at this particular section, I will just find out the value of AST, and we have already seen that the AST is 3 times pi by 4 into 25 square. Then I will calculate 100 AST by BD based on that. Then I will find the value of tau c from table 19. Also, I will calculate the value of tau c max from table 20. So once I get that, I will just perform this check whether shear reinforcement is needed or not. And in this particular case, I can see that this is the condition where I need to go with shear design. So basically, in the next step, what I will do is that what is the amount of shear force? I have a total shear force of, as given here, 244.2 to be resisted. Out of this, how much can be taken up by my concrete section? That is what I am interested in. So basically, first of all, I have to calculate how much shear force can be taken up by my basic concrete section. That is given by BUC. This is concrete section. Okay, BUC, which is equal to tau c into B into D. Tau c is already calculated here. Substitute these values and we can see that 103.68 kilonewton can be carried by my concrete section alone without the effect of bent up bars or stirrups. Okay, now remaining part I have that force, that is out of this 244.2, 103.68 is safely taken up by my concrete section alone. Now for the remaining force, I have to actually provide the stirrups, as well as I can take up the help of bend up bars also in this particular problem. So I need to first of all find out how much is that remaining quantity. So that is the quantity that should be resisted by the stirrups and bend up bars. Therefore, VUS is equal to the amount of shear force in total we have minus the amount of shear force that is taken up by my concrete section. So 244.2 minus 103.68, which is obtained from here. Okay. So after substituting that, I can see that the net amount of shear force I should resist with the help of stirrups and bend up bars is 140.52 kilonewton. So we have to perform the shear design for this load. Is that clear? Any doubts? Can we proceed? Okay. I hope it is clear to you.
Sir.
Yeah. Ask. Please ask.
VUS പറഞ്ഞില്ലേ? VUS പറഞ്ഞത് WL/2 minus WL അല്ലേ അവിടുത്തെ ഷിയർ ഫോഴ്സ് എന്ന് പറയുന്നത്?
അതെ.
W into D. W into D.
Right.
അപ്പം നമ്മൾ ഫാക്ടർ ചെയ്ത് വെച്ചേക്കുന്ന അത് അതേ മൈനസ് ആണോ?
അതിലെ കൺഫ്യൂഷൻ വരല്ലേ. നമ്മൾ ഇവിടെ ചെയ്തതെന്ന് വെച്ചാൽ നമ്മൾ ലോഡിന് ആദ്യം തന്നെ അങ്ങോട്ട് ഫാക്ടർ ചെയ്തു. പിന്നെ ആ ഒരു ലോഡ് യൂസ് ചെയ്തിട്ടാണ് നമ്മൾ VU ആയാലും ബാക്കിയെല്ലാം. ഇപ്പൊ ഇവിടെ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യണ ഈ W ഇല്ലേ, ഇതെല്ലാം നമ്മൾ ആ ഫാക്ടർ ചെയ്ത ലോഡ് തന്നെയാണ് സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യേണ്ടത്. എന്നാൽ മാത്രമേ നമുക്ക് ഫാക്ടർ ചെയ്ത ഷിയർ ഫോഴ്സ് കിട്ടുള്ളൂ. എങ്ങനെ വേണമെങ്കിലും ചെയ്യാട്ടോ. അത് പ്ലീസ് അണ്ടർസ്റ്റാൻഡ് ദാറ്റ് ഐദർ യു ക്യാൻ ഫാക്ടർ ദി ലോഡ് ആൻഡ് ഡു ദ റിമൈനിങ് കാൽക്കുലേഷൻ, അല്ലെങ്കിൽ ചെയ്യാവുന്ന ഒരു പരിപാടി എന്ന് പറഞ്ഞാൽ നിങ്ങൾക്ക് ഇത് VU ആയിട്ട് തന്നെ കാൽക്കുലേറ്റ് ചെയ്യാം. ഫാക്ടർ ചെയ്യാത്ത ലോഡ് ഇന്റൻസിറ്റി by 2 minus W into 0.6 ചെയ്യുമ്പോഴേക്കും നിങ്ങൾക്ക് factor ചെയ്യാത്ത shear force കിട്ടും. Then what you can do is that you can find the factor shear force by just multiplying the shear force with load factor 1.5.
അപ്പൊ ഇവിടെ ഇല്ലേ, അപ്പൊ ഇവിടെ 333 മൈനസ് നമ്മൾ ഫാക്ടർ ചെയ്ത് വെച്ചേക്കുന്ന 111 into 0.6 അല്ലേ വരുന്നത്?
333 minus 111 into 0.6.
266.4 ആയിരുന്നു. ന്യൂമറിക്കൽസ് വ്യത്യാസം ഉണ്ടായിരിക്കും.
Don't mind that. Okay. Okay. About the clear ayallo? Is there any more confusion in the procedure? Okay. So let's proceed. So till now we have calculated the amount of shear force that will be taken by my concrete section as well as the amount of shear force for which I have to perform the shear design, and that value is 140.52. Let's take it as 140.52 itself and proceed. Now in the next stage what we have to do is that as per our code, when we have say single bars bent up bar, we have the equation BUS is equal to 0.87 Fy into ASV into sin alpha, right? I hope you remember this. We were having three conditions, and in that we were having one condition where we have a series of bent up bars bent at the same section. A series of bars bent up at the same section. We had two conditions. First condition is bent up bars or a series of bars bent up at the same location. Then we have another set of condition where we have bent up bars at different location. Okay, in that this particular problem is our first case. That is where we have the number of bars bent up at the same location. Okay, at 1 meter distance we are bending up 2 bars. That is the only bent up bars we are having. Okay, so I am using the same equation here. VUS is equal to 0.87 Fy ASV into sin alpha. In this you know the value of Fy, you know the value of ASV, you know the value of alpha. Let's take alpha as 45 degree itself. And how to calculate the value of ASV? What is this ASV in this particular case? ASV means it is the shear reinforcement, and in this particular case we are considering this 2 bent up bar as our shear reinforcement. Therefore we have to take up the cross sectional area of this bent up bar. Please note this is a major area where students commit mistake. In all the equation for calculation or the design of shear, ASV is the cross sectional area of shear reinforcement. In this particular part we are actually using these 2 bent up bars for resisting the shear. Therefore the cross sectional area of this bent up bar must be substituted as ASV. That is why they are calculating ASV is equal to 2 into pi by 4 into 25 square. We know that this 25 mm bar was actually bent up in the form of bent up bars. Find this value, substitute it here. You know the value of Fy, you know the value of alpha. Let's take it as 45 degree. So please calculate this part, and that will give the value of shear force that can be resisted by with the help of these 2 bent up bars. And in this particular case, when you substitute this, you can see that this value is coming like this. That is around 250.63 kilonewton. So what was the value that we should resist or we have to perform the shear design for? It was just 140.52. Okay, but the capacity of these bent up bars is 250.63 kilonewton. So can we stop here, because it is actually safe, right? We need to resist only 140.52, but here the capacity is 250, so it is safe. Can we stop it here? No, we cannot stop it. The reason is that if you go to your code and refer the clause corresponding to your shear design, there was a note given. I think I haven't discussed that earlier, so let me try to take the IS code. So at this part, so basically in page number, I hope you are able to see this PDF, right? It is clear to you, right? Yeah. So before these equations, you have a clause here where bent up bars are provided. Their contribution towards shear resistance shall not be more than half that of total shear reinforcement. Okay. So basically the idea is like this. In this particular case, we need to actually resist a total shear force of 140.52 kilonewtons. Okay, so what they suggest is that we can utilize the effect of bend up bars, but this should be utilized only to a maximum of half of the total load that should be resisted. Again, I am repeating, the effect of or the contribution of bend up bars can be utilized only to take up half the amount of total load that is to be resisted by shear reinforcement. In this particular case, our total load that should be resisted by my shear reinforcement is 140.52. So I can use this bend up bars to resist a maximum amount of half of 140.52, that is 70.26. I can utilize the bend up bars for taking up only a load of 70.26 kilonewton. Even though it is having capacity to take up 250.63 kilonewton, as per the clause of our code, we can utilize this bend up bar only to take up a load of 70.26 kilonewton. Is that clear? Is that point clear to you? Any confusion or any doubt in that? Okay. So now what we need to do is that initially we were supposed to design shear reinforcement for 140.52. In this, 70.26 can be given to this bend up bars. It is having more capacity that you just neglect. As per the code, we can provide only 70.26 kilonewton to this bend up bars. Now we have a remaining load of again another 70.26 kilonewton. For this, we have to provide stirrups, additional stirrups. Okay, this is how you should proceed with your shear design. Now, the remaining BUS is 70.26 kilonewton. For that we will provide the vertical stirrups. Okay, now we will come with the usual procedure which we have done in the previous problem. So basically now the BUS value is 70.26. Now what we can do, we have the equation BUS is equal to 0.87 Fy ASV into D by SV. From this we will take the SV to the other side. Now we have 0.87 Fy. Here what will be the value of ASV? Here we should assume, same here we are using 8 mm dia, 2-legged stirrups. Therefore ASV will be equal to 2 times pi by 4 into 8 square. Substitute that here. D is known to us, Fy is known to us. What is the value of VUS? VUS is this quantity, 70.26. Now you find the value of the new SV. Okay, so from this SV will be equal to 310 millimeters. So basically we have to provide only 8 mm diameter 2-legged stirrups at a distance of 310 millimeter center to center. Again, the clause of code comes into picture. As per the code, we can provide only a maximum spacing of minimum of 0.75 D or 300 millimeters. So when you calculate this, you can see that this value is a larger quantity. So what we have to do, we have to provide 8 millimeter diameter 2-legged stirrups at 300 millimeter C by C. Is it clear? Any confusions? So this completes the shear design at our first section. Now, right now we have taken only one section. That is that was the section at that was our critical section. So we have now performed the shear design at the critical section. After this, at the center, we know that in this particular problem, we have a simply supported beam again carrying a UDM. So at the center, the value of shear force will be anyway 0. So even though the value of shear force is 0 as per our clause, unless our tau v is less than tau c by 2. I hope you remember that there was a note given in the clause in your IS code that when the value of tau v is less than tau c by 2, you need not give this minimum reinforcement also. But in this case, that is not satisfied actually. I think that is not satisfied, right? When the value of actually the tau v value when you calculate, it may not satisfy. Tau v is actually coming as 0 right in this particular problem. Anyway, if it is 0 also, here what they have done is that they have just provided the minimum amount of shear reinforcement. So let us see what is the procedure for providing the shear reinforcement. We will be having, actually our main aim is to understand the concept or the procedure in which we have to design for shear. So please understand, at this particular section, the value of shear force is very minimum. So if you are calculating the tau v and proceeding, then also you will, in this particular case, you cannot do because the value of shear force is actually 0. Anyway, say, let us assume that we have a case where tau v value is less than tau c. Tau c is actually larger than the tau v coming at this particular section. In that case, what we have to do is that we have to go with minimum shear reinforcement, right? So for that, what you have to do is that you have a clause in clause number 25.5.1.6. I hope I am correct. So please verify that. There you have the provision for providing minimum shear reinforcement. So there basically what you have is this equation: ASV by B into SV should be greater than or equal to 0.4 by 0.87 Fy. Please note this Fy is actually the grade of steel that you are using for your stirrups, not that of flexural reinforcement. Okay, and again this ASV is the area of cross section of your stirrups, and again not that of your flexural reinforcement. So please don't confuse with this. These are the common mistakes that students commit during your examination. That is why I am stressing here. And now what you have to do is that you just again, as you have done in the previous case, take the same diameter and number of legs for your stirrups. Then you provide the value of ASV. You have the value of B. You have the value of Fy, and find the value of SV from here. Then check with the maximum spacing provisions, and you provide the minimum of that.
Sir.
Yeah.
ഒരു സെക്ഷനിൽ ടോവിന്റെ വാല്യൂ ടോസിന്റെ ഹാഫിനെക്കാട്ടും കുറവാണെങ്കിൽ കൊടുക്കണ്ടെന്നല്ലേ റീഇൻഫോഴ്സ്മെന്റ്? ഈ കേസിൽ 0 ആയിട്ടും നമ്മൾ
കൊടുക്കുന്നുണ്ട്. അതിന് റീസൺ ഉണ്ട്. ഞാനത് കൂടുതൽ കൺഫ്യൂഷൻ ആകണ്ടെന്ന് വെച്ച് പറയാൻ ഞാൻ I will explain that anyway, as one of you asked this. I will explain it. So once you have a beam like this, we will have the maximum shear force at the supports and minimum 0 value at the center. Then we have again maximum at the other support. So basically you will have the variation like this, right? So right now, even though we are just taken the section here, and here the shear force is actually 0. And finally what we will be doing towards then, what we will do is that we will provide a statement like this, that is provide 8 mm diameter 2-leg stirrups at some spacing. So if you are taking into consideration that the shear force at this particular point is 0, what will happen at this section? Say, let me take another section at very near to this one. Okay, I am considering a second section to the left of this. Here I have some sort of shear force, right?
Yes, sir.
Am I correct? Yeah. Yes. So basically here you will be having a smaller value for this tau v. And when we compare this tau v, it may not be less than half that of tau c by 2 in this area, maybe here at the midspan. So basically what I am trying to explain is that the result of our shear design will be something like this: 8 mm diameter 2-leg stirrups at some spacing. So basically we are not just providing the reinforcement at this particular section alone. What we are doing here is that we are actually telling that we have to provide n number of shear reinforcement at a particular spacing like this. So it will be extending to some distance to this side as well as some distance to this side. So once you are focusing on the thing that the here shear force is 0, so tau v will be 0 and it will be less than tau c by 2, and you are not performing the shear design at this location, what will happen here? Here you have some shear force, so there can be failure happening at this particular location. So that is the reason in this particular problem we are actually designing the shear reinforcement. We are actually providing the minimum amount of shear reinforcement at the midspan section, even though the value of shear force there is 0. Is that clear to you what I was trying to convey?
Sir,
yeah, the only thing is that even though at this particular section at the exact midspan we have a 0 shear force, the amount of shear force in the nearby section is not 0. Here and all, it is not 0. So once we are performing a shear design, what we will finally do? Say, let us take the previous case. We have a critical section like this, and we have designed the shear reinforcement here, and our answer was like 8 mm diameter stirrups, 2-legged 8 mm diameter stirrups at 260 center to center, right? So
Yeah.
how you will provide this reinforcement? Will you be restricting the reinforcement only in this particular section, critical section? No, you won't be doing that. What you will be doing is that you will be providing this 2-legged 8 mm stirrups at a spacing of 260 center to center. So you will provide your first stirrups here, then you will take 260 millimeters. You will provide another stirrups here, then again you will take another 260. Then you will provide the next stirrups. Like that, you will continue. So basically, this is actually performed for an area, a sufficient length. You will be providing shear reinforcement at the same center to center distance, and again 2-legged 8 mm stirrups. In a similar fashion, once you perform the design at this mid span, you won't be restricting your shear reinforcement only in this section. You will be providing it to the left as well as to the right. But here and all, you have some value for your shear force, so that will cause a value for your tau v, which may not be less than tau c by 2. Okay, so in order to account for that, we are actually providing the minimum amount of shear reinforcement in this locality. Suppose in a beam, you have a case like this. You have shear force. I am just drawing the shear force diagram. You have a case like this, and if you see, for this much span, you don't have any shear force. In this particular case, at these mid areas, you may provide no reinforcement. You can avoid the presence of shear reinforcement, because to a larger area, you don't have any shear force acting there. Is that clear? That is not the case here. Here the case is different, because here only at the mid-span section we have zero shear force. Just to the left, maybe 1 centimeter to the left, you have some amount of shear force. Also 1 centimeter to the right, you have some amount of shear force. And again, as you go further, your value of shear force will be increasing. Now, is that clear? Should I repeat it?
Yes, sir. Clear.
Now, once this is done, so what right now we have in our hand is like this. So all of you, please listen now. Please stop writing and listen here. I hope I am audible. I am not mute, right?
Yes, sir, we can hear you.
Yeah. Okay. Yeah. So basically, what right now we have is like we have again it is. We have a beam like this, which is having some span of 6 meters, and right now we have performed 2 design, one at the one here, a section here, and another one here. That is at the critical section. So you have 2 results at this particular point. Say let me name it as AA, and let me name it as BB. Okay, I'm taking 5 more minutes, so please cooperate with me. So at this section AA, you have obtained it as something like a 2-legged 8 millimeters phi at 260 millimeters center to center, and at the midspan, that is at the section BB, what you have obtained is 2-legged 8 mm phi at 300 millimeter C by C. So my question is, say, how long will you extend this thing? First result. Say here you are actually providing your stirrups at a center to center distance of 260 millimeters, but at the midspan you are providing a center to center distance of 300 millimeters. So where this transition will occur? That is my question. Say at a particular distance, say let us assume it to be X from your left support, we can change the spacing to 300 millimeters. How we can find that?
Sir, നമ്മള് 1 meter കഴിഞ്ഞപ്പോഴല്ലേ നമ്മളത് ബാർ ബെൻഡപ്പ് ചെയ്തത്. അപ്പൊ അവിടം വരെ നമ്മള് ക്രിട്ടിക്കൽ സെക്ഷനിൽ എടുത്തത് അപ്ലൈ ചെയ്യാൻ പറ്റും.
Okay, ശരി. Any other answers? So okay, so as you told, so in this particular case, what here they have done is they have again performed another set of design at 1 meter from the left support. As you told, we have a provision of bent up bars at a distance of 1 meters. So let me assume that 1 meter is actually coming somewhere here, and I have just bent up my bars and right now I have performed a design at AA, and I am providing that up to this point. At this particular point where 1 meter is reached, I have 5 number of 25 members going in this horizontal direction. So basically what you have to do is that you have to take another section here, say let us mark it as some CC, and you have to again perform the shear design, and let us see whether the spacing can be increased to 300 at 1 meter spacing. Okay, so but in this particular case also, I don't know whether this numerical value is correct. I am getting, let us assume that for our problem also we are getting a numerical value like 220 millimeters. It is not coming to 300 millimeters. We are getting a higher value here also. So in such a case, what you can do? See, at 1 meter also, you are not getting 300 millimeter spacing, but at the mid span, you have obtained 300 millimeter spacing. So in such a case, what any suggestions from your side? As a structural engineer, say I am seeing you as my young budding structural engineer. So what is your suggestion from your side? And again, there is nothing new, just purely mathematics. That's all. So we don't know actually from where this transition will occur. So let us assume it as x distance. Okay, from left part, I am just taking x distance, and I am considering a section. Say let us mark it as DD. From this section, let us proceed. Let us hope that we will be able to proceed with 300 mm spacing, center to center spacing. So what is the factor that will contribute this or influence this one? Basically, if we are decreasing the center to center spacing, the amount of shear reinforcement will be more. If you are increasing the center to center distance between stirrups, the amount of shear reinforcement, effective shear reinforcement will be less. When will we reduce the spacing? When we have a huge amount of shear force to be resisted, the amount of shear reinforcement must be more. So we will have a smaller spacing. As you can see, at the critical section, in your case, you obtained a spacing of 260, where you have a higher amount of shear force. Towards the middle, you were having only a lower amount of shear force, so you obtained a spacing of 300 millimeters. So basically, the main significant factor is your shear force, which will contribute to this spacing. Am I right? If I am wrong, please stop me. Am I right?
Yes.
So this is what is significantly influencing. So what we will do is that, as I told, I have already made an assumption that this transition is occurring at a distance of x units. So what I will do is that in the same beam, I have a support reaction here, which was equal to WL by 2. Then I was having a UDL. Since I am considering a section at a distance of x units, I again have this UDL here. Okay. So in the first stage, what I will do is that this distance is assumed to be x. Then I will calculate the amount of shear force coming over here, VU value. So that will be this WL by 2 in the upward direction, and the effect of this UDL in the downward direction. So that will be WU into L by 2 minus W into X. I will get a term in terms of X. Am I correct? Now what I will do is that I already know at this particular section what is the capacity of my concrete section, that is VUC, which was already calculated in the previous part. Now in the next stage, what I will do is that what is the amount of shear force that should be resisted by the stirrups at this particular section, that I need to calculate. So I will take the difference of total shear force, that is 333 minus 111x minus the capacity of my concrete section. Okay, same procedure. Then what I will do is that I will just substitute this VUS in our main equation, that was this one. Here I will substitute this instead of this VUS. What I will do is that I will substitute this term, this VUS, that is in terms of x. This thing I will substitute in my equation there. Let me see whether I have, yeah, I have it here. So instead of this VUS, I will substitute this value, that is 208.44 minus 11x, which I obtained as my VUS. Then I know the spacing. So at this particular section X, what happens? The spacing between the stirrups will be converted from 260 to 300 millimeters C by C. So I have my spacing before in my hand. So basically I will substitute the value of 300 as my spacing. I will substitute VUS in terms of X. Then I have the value of Fy, I have the value of ASV, I have the value of D. So the only unknown in this one will be my X, and upon simplification of this, I can easily calculate the value of my X. Is that clear? Is the procedure clear? Any doubts? Oh, sure. So basically, for our beam, we have two results for our shear design. Okay. We have two values, one at the support section and another one at the midspan section, and we are interested in finding out from which location I can use the center to center distance of 300 millimeters. I am interested in finding this location. So right now I don't know the value of this location, so I will just assume it as X units from my left support. Okay, now in the first stage what I am doing is I am just calculating the amount of shear force that is acting at this particular location, that is VU at this X. Okay, how I can find this? I know that I have a support reaction here which is equal to WL by 2, and again in this beam UDL is acting throughout the span. So since I am interested in this section, I have to consider the UDL acting up to this section. Okay, so this will be again W. So basically the shear force at this location will be WL by 2. It will be WL by 2 in the upward direction minus W into this distance, that is X. That is what written here, WL by 2 minus W into X. And so I obtained a expression in terms of X as my shear force, total shear force coming at that section. In this total shear force, some amount of shear force will be taken up by my RCC section. Flexural, after flexural design, we have obtained a section now consisting of 5 bars of 25 mm diameter at this particular point. So this section will be able to take up some amount of shear force from this total value. So I have to find out that. And already in the, when you perform the minimum shear design, you have obtained the value of VUC. You have already calculated that, that is coming around some value. You might have obtained some value. In this particular problem, they have given it as 124.56 kilonewtons. So basically the difference between these two should be resisted by my shear reinforcements alone. Okay, so basically that quantity will be the difference of these two, that is 333 minus 111x minus the capacity of my concrete section. So again, I have obtained the amount of shear force that should be resisted by my stirrups in terms of this distance X. So this is an unknown quantity for us right now. But we already know that at this particular section, our spacing can be taken to 300 mm center to center. Okay, so now coming to this equation, instead of this VUS, I will substitute the value in terms of X. So this is the amount of shear force that should be resisted by the stirrups at this particular location, which can be substituted as my VUS. And again, I know the value of SV, that is the center to center spacing of my stirrups, because at this particular section we know that the spacing will be converted to 300 mm center to center. So I can substitute, instead of SV, I can substitute the value of 300. All the other values are known to me. Only unknown is the X, which is coming in this VUS. So upon simplify, you can take this part to the left and bring down this 300 in the denominator, and finally you simplify and find the value of X, so that at that distance from your left support, you can convert the spacing from 260 to 300 mm center to center. Is it clear now? Any more doubts?
Yes, sir. Yes, clear.
Okay. So towards the end, once you complete up to this part, what you have to do is that you have to give it like this. Say from 0 to 1 meter. So we have performed 3 design. One is at the critical section, one is at the midspan, then at 1 meter distance. Okay. So from 0 to 1 meter, we can easily give 2-legged 8 mm diameter stirrups at a spacing of, no, this is wrong actually. 0 to 1 meter, it will be your 260. In your case, it is 260 mm C by C. Then from 1 meter to this X value, you will be getting some value as X. So from this 1 meter, so basically it is like this. You have your beam. From this 0 to 1 meter is your first case. Then from this 1 meter to your X distance. Okay, this is up to 1 meter. So this is 1 meter. Then from this 1 meter to your X, the value of X which you have already calculated. So this will be your X. Okay, you can provide the second value which you have already obtained when you have performed the shear design at 1 meter. At 1 meter also we need to provide a shear design. So after that can be given in your second line. And finally, the value of shear design which you obtained at the midspan can be given for the remaining. That is, from this X up to the midspan, you have to actually provide the spacing of 300 mm C by C. So this is how you must complete this problem.